I'm Viraj Purang. I am going to give this talk on a Clojure DSL for defining CI/CD orchestrations, something we use at Oracle where I work. I have my colleague, Rohit Kumar, who's going to be helping me with the second part of the presentation. And we work for a central engineering team within Oracle. We do basically services that improve developer productivity and enhance quality of a bunch of stuff that we do as developers. We're quite centrally focused on continuous integration and delivery, a lot of DevOpsy stuff. So I'm a little nervous. So if I do stuff that I'm not supposed to do, I hope you guys are okay with it. So this is a safe harbor statement I just have to show as an employee. And I'll quickly go through the introduction. So we'll go through the motivation of why we did this particular thing. There's a detail about orchestration service for defining the CI/CD pipelines that we'll go through. We'll discuss the architecture a little bit. And then Rohit will discuss the more specific details about the DSL and what our experience has been in terms of just using Clojure in general. We started off, at least I started off as a Java developer. He's one of the few, I guess, in the world who started off on Clojure, so he's got a very different perspective on Clojure. So I'll just go to the next slide. So there's some history behind why we did this particular product. We have diverse distributed systems with a lot of scale. So when I'm talking about scale at Oracle, we're like, we have an Artifactory instance, which is probably the biggest one in the world at this point of time. We have about 100 terabytes of installers and a bunch of other stuff that's stored in it. And that's just one of the systems that we typically work on. There's like hundreds of other things that typically get added as a part of our development process. So if we are doing CI/CD, if we are doing any Jenkins or Hudson or TeamSite or TeamCity jobs, they translate to pretty long pipelines. And those pipelines, they can span like, I don't even count the number of development teams that are out there. They're pretty diverse. There's stuff that happens on Node.js. There's stuff that happens on Java, Clojure, pretty much any technology you can think of. And the development tools get burdened. So, like if you really want to stress test any piece of software that you made, send it to us. We'll break the hell out of it. It's that bad. And the scale and the visibility of any one of these pipelines is a little hard to do because there's a lot of things that, a lot of like heterogeneous things that you need to look at. And so visualizing them across the board becomes a bit of an issue. And those are the 4 or 5 basic points that we started off with when we started doing serious CI/CD from a corporate perspective at Oracle. So when we began CI/CD, the biggest question we had was, are we going to be able to scale? We started off with one Hudson instance. We also have Jenkins in the play. And the answer was no. There were about 100 teams on that particular Hudson. The problems were not limited to what I'm going to talk about, but 2 different teams want a different version of the installer. Someone wants to install something, so the Hudson has to be brought down. And now you have 100 teams that are not working at the same time. So we took our next logical step, which was to distribute it across different instances of the CI/CD tool that we were using. And it was all good. The only problem was, how do you link anything from one system to the other system? So if we have a a particular pipeline that goes from one Hudson instance for WebLogic server and wants to do something for TopLink, which is another product that they had, how do you make sure that you can actually trace an issue that happened on a TopLink server back to the WebLogic server that's out there? And even if you were to somehow figure out a way of doing that, you want them to be able to visualize that. Not everyone is a developer. Not everyone wants to actually go on, log onto a box, see what's going on. So we had to come up with something that would actually work. This is yet another slide that describes the different things different stakeholders we typically have. So there's developers, which is fairly obvious. There's doc and translation, which is, so if we have manuals that we want to expose to a bunch of customers for different products that we sell, we have to make sure that they're available for each and every different language. So that's what doc and translation is. There's a patching framework that we have, which manages different kinds of patches that we send out for different products. And they have a separate kind of requirement where the servers that they're on need to be more dependable. They cannot be down, because if we are unable to deliver a patch to one of our customers, it's money lost. Then there's the problem of global scale. So our data centers are pretty much everywhere in the world. And we had to make sure that whatever we have, whatever pieces of build pipelines or testing pipelines we integrate, they're able to scale across different data centers. Then there's obviously other things like cloud that we deliver to. There's on-premise releases that we needed to manage. And then there's the multiplicity of different CI/CD products. So we currently support Jenkins, we support Hudson, we support different versions of them, and we also support TeamCity. So all of this, the combination, the fact that we had diverse set of stakeholders, it created a situation for us which was hard for us to solve using direct code-to-code invocation. And so we had to switch to something that would allow us to orchestrate across all these diverse set of systems that were out there. And so we came up with this product called Carson. And you might ask what Carson really stands for. And it's a Downton Abbey character, which is supposed to be a butler of butlers. And the play was that Jenkins and Hudson are both butlers, and this is like the butler of butlers. So Carson seemed like a nice name to give. It was actually done by a colleague of mine who now works at Atomist. His name is Jim Clark. He was also responsible for starting this project initially. And very quickly, it became an event-based orchestrator, which allowed us to integrate all of these different components that are out there. So if you were to just go underneath the hood and look at what it is, it's an orchestration engine. It allows you to orchestrate workflows across diverse distributed CI/CD systems. It's event-driven. And the event sources can be fairly dynamic and fairly diverse. So we have, at the last count, probably 6 different source control management systems. Multiple Jenkins Hudson instances, test tools. We have test farms, Mesos, Kubernetes. We're using pretty much everything that's out there. And the events can be consumed from messaging systems like ActiveMQ or Kafka or RabbitMQ. Or you could just send them on webhooks that are a part of Carson. And what that allows us to do is basically have systems that would normally not be able to send a message to a messaging system like ActiveMQ, could just send or post a message to a HTTP endpoint, and that would be the end of it. Now, there are a couple of terms that I'm going to introduce right now, which will be quite useful when Rohit starts talking about the DSL in more detail. So orchestration or a pipeline or a workflow will be used interchangeably. And the instance or an orchestration instance is the same as a single run of a pipeline. And the pipeline is pretty much the same thing as what you would expect on Jenkins or Hudson. It's a bunch of jobs that are strung together. The only difference here being that the jobs can be from different systems. It's not limited to just one system. So since we are talking about events, this is just a simple event. We don't enforce any schema on the events. And at least at this point of time, we don't. It's fairly simple. Like if you look at a Jenkins event, it contains a root URI, which is the URL of the Jenkins instance. What kind of an event it is. So on finalized is when the finalization happens on a particular job. Then there's job-specific details like job number, status name, and the ordinality. And then there is a map where we have key-value pairs. Now, this can be different for Hudson. This can be different for pretty much like whichever job system we are planning to use. And the idea here is that we can curate the event streams, the job systems, like pretty much anything that is needed for the pipeline. And here I'm going to just talk a little bit about the architecture. So you can see these different components. Each one of them is an event stream. So Hudson and Jenkins are fairly obvious. We support Mesos and Docker Artifactory events. So anytime there's an update or there's an addition to Artifactory, we're able to emit events from there. And then we have more internal tools like test farm and docs and translation, something that I talked about in a previous slide, source control management systems. All of these act as event emitters. And then they send messages to the messaging middleware. And we currently support all 4 of these. Actively, I guess, only RabbitMQ and Kafka, but Cupid and ActiveMQ have been supported in the past. And the Carson core itself it consists of these 6 or 7 different components. There's job systems. So each one of these components that you see on the left side as event streams are available to Carson as a job system. And for you to be a job system, there's only 2 things that you really need. One is that you should be either able to emit the event to us, or and you should also be able to provide us an endpoint where we can actually invoke you back. There are variants of this where there are some things that are only event emitters, and there are some things that are in that particular there are things that are only event emitters, and then there are pieces that only have endpoints. So we just send specific calls to them. But general idea here is that if you're a job system, you should give us both the capabilities. Otherwise, we'll have to poll or do something similar. The DSL, which is the meat of this engine, is a combination of or collection of handlers. It's event handlers. And orchestration server is where these handlers are loaded from the database. The system started off as a provisioning engine where we could provision multiple masters or create the integration between them. So there's a provisioning aspect that is available. And then we have a REST API and a UI, fairly basic, but something that allows us to do the job. And then there are value-added services like configs, visualization, and analytics. We store our configs. We've externalized them into a etcd database. The visualizations are actually done using D3, and the analytics is done currently using Angular. There's a bunch of web pages or screens that we have which actually do that. But there's an additional element where we depend on the BI services that are offered by different Oracle BI products. The simple idea here is you send an event, and it could be sent either to a webhook or through an AMQP broker. This animation just shows the aspect, and wherever there's an endpoint, we trigger jobs using the REST API. So for example, if it's a Hudson job, there would be an endpoint which would allow us to trigger a job on Hudson. Similarly, if you're sending the message to a webhook, the concept is still the same. We just send a JSON payload to that particular endpoint, and that triggers the downstream workflow. And just to give you an idea about the scale, there's a significant volume that we typically drive during the day. There's about 100,000 events that are triggered during the day. And these events can be Hudson or Jenkins events. There could be test or farm events where, if the tests get executed, depending on the life cycle of those tests, each one of them emits a different kind of an event. We share slaves between our Hudson and Jenkins instances. We use Mesos for doing that. But we have close to 600 slaves, so you can imagine even if you have 10 jobs per slave, that's a fairly high number. And we run about 1,800 orchestration instances per day. There are 500 different orchestration definitions that are currently available, and the number is only going up. So that's pretty much it from my perspective. I think I've given a general idea about the architecture of the tool. He's going to just go into the DSL specifics and a little bit about the Clojure, why we chose Clojure, and what we are doing with it right now.
Check. Yeah. So now that Viraj has covered most of the architecture and the motivation behind, why we created this service, I'll be concentrating on the DSL itself and the Clojure aspects of it. So the domain-specific language, in our case, the domain was creating pipelines that span these diverse CI/CD systems. So to create the DSL, we defined some of the basic primitives for the DSL. Now, what an orchestration is just a namespace. So it's loaded, it's a Clojure file. You use the DSL to define your orchestration. And it's loaded into a unique namespace using create_ns and gensim. So it gets its own unique namespace, and all the constructs from the DSL are available to it. So an orchestration, essentially, just to reiterate, is a set of event handler definitions. And the DSL is able to create those event handler definitions. It is represented as a directed acyclic graph. And again, an instance, which is a single run of the pipeline, is a sequence of transitions or handler executions. Now, what is the basic event handler definition that we provide? Most of our basic event handlers are composed of 3 parameters. The first is the event or the event channel or a specific job. So every handler is activated when an event arrives and matches the event that you declare in your handler. The second element is predicates, which are a list of functions that are designed to work on the events. So if you spec them, they are functions that take a map as an input, and they are designed to work on specific as well as general event types. Actions are where we further dispatch tasks or submit jobs, and that's how the orchestration or the workflow proceeds forward. So for example, submitting a Jenkins build or submitting a Mesos task. So just a little bit under the hood, what happens, all of these handlers, so when you create your orchestration, it results in a registry of handlers for that specific orchestration. There's no memory footprint when an orchestration instance is running. The handler only gets activated when a particular event arrives and it satisfies the predicate for a specific handler. So just to walk you through the workflow, an event arrives from the messaging layer. The engine finds all the handlers that are correlated or waiting for that specific event, and then it runs the predicate functions to check if they are logically true. And if it is, then it proceeds to the actions, right? Now, these are the basic handler types that we support. Now, because an orchestration is just loaded into its own unique namespace with the entire DSL available, at its simplest, it's just a Clojure module, and the simplest orchestration that you can create is just a comment, just nothing. Anything that can be loaded using load string, you can do that. So these are the primitive DSL handlers with which we built the entire DSL. You can compose all of these together. You can use these as templates to create further DSL elements. So just to briefly give you the signatures, the API signatures of all of these DSL macros, DefStart expects, if you look at each of them, they expect, in almost all of them, they expect three things: the event or a particular job, a list of predicates, and then finally a body which corresponds to actions. Let me briefly show you an example. So DefStart is a handler designed to is designed as an entry point to your orchestration. So this is when your specific run of your orchestration can get triggered. So DefStart is an indirect trigger. An event arrives, it ends up triggering an instance of an orchestration. If you look at the bottom, there's a def trigger as well, which is a more targeted endpoint. So given an orchestration, you want to you want to only trigger an instance of that orchestration. In that case, this is what you'd use. So in that case, there is no event channel. It's just the channel is the org-specific channel that we use. When I talk about channels, it's the event stream. So the channel, all events correspond to code.async channels, and that's how the handlers consume them. So DefStart is an entry point handler that is more that is suitable for indirect triggers. So for example, you're getting events from a GitHub repository. This is the form you'd use. So if you look at the from, the first element, the from defines the event channel. In this case, it's a channel called Git. It corresponds to a named code.async channel called Git. So an event comes in, and then the second element is the list of predicates. So the list that you see here is two different DSL predicate functions. And the first one is simply checking in, like, if I just say it in words, it's checking whether the organization for that GitHub repository on the central Git repo is my org. And the second is checking whether the project in that SCM event is for a Git project called Terminator build, right? So if you look at these predicates, again, as I previously mentioned, the spec is that it works on, it's applied on the event. So we would apply git org is equal to my org. That results in a function that expects just one argument, which is the event in the context. So this returns me a function. I run it on the event that came in on the Git channel. Events, again, are maps, right? So it's very easy to just filter based on them. Git project, again, does that. It is applied on the SCM event that came in. And then we logically AND them together. If all of that is successful, you proceed to the action. So you trigger the callback in that sense. And yeah, so the then section is where the actions are. This one just has one form here. Most of the action block is an implicit do block. So you can define multiple actions. You can trigger multiple jobs. You can dynamically trigger jobs as well, which I'll come to in a bit. But this is a very simple example where an SCM event comes in, you trigger the build CI job for that particular project. The key things to notice, which I'll show you here, is, yeah, just to reiterate, the handler is DefStart, the channel is the event channel, these are the predicates, and the action block is here, right? Now let's take a look at one of the more common handlers that stitches the pipeline together, which is a DefTransition. So this you usually end up using once you all have already defined a DefStart, and a DefStart has already been activated via an event or in a more targeted fashion. So in the previous slide, we introduced the concept of handlers, but what I'll try to focus on here is some of the terminologies again. So if you look here, in this case, the from is a label. It's not an event channel. It's a more correlated job label. So when you triggered a particular job here, you added a label called ID build for that job, and you're able to use it in your handlers as you go through the pipeline. Now that's one of the things that we check, which is that these labels are unique in the context of a specific orchestration, because they correspond to node names in your directed acyclic graph, right? This is the thing that is used. This is the glue that stitches the whole pipeline together. So we do compile time checks when the handler is registered that these are valid. Now, of course, because this is just a Clojure module, and we are not blocking you from creating, running Clojure in here, there are cases where there needs to be, at compile time, we do not know the job label or the correlation IDs. Okay, just again, same handler, same concept of 3 different requirements. Now, our orchestration, as I previously mentioned, is designed for directed acyclic graphs, so it's something that proceeds forward. So these are parsable, like these are parsable expressions. So we use Clojure.work to be able to construct the graph at static time, as well as for a specific instance, we are able to based on the transitions that happen, we are able to construct the graph. So very simply, if you look at this handler in terms of what it corresponds to as a graph, so ID build happens, and then we start a job called test job 1. We also start a job called test job 2. Both of them happen in parallel. And the DefTransition handler is the one that ends up as defining the edges between these 2 nodes. If you look here, there's also this thing called in-group, which you can use to group, add labels over groups of jobs, which helps in terms of like dynamically starting jobs. So if you're not sure of the number of jobs you'll start for a specific instance, but you want to respond to the whole set of the jobs, that's what you'd use. Just proceeding quickly through some snippets of the DSL, just so that it registers. So this is another DSL element, the first one, where you're able to trigger an instance of another orchestration in that same orchestration server, or another server. All we require, because orchestrations are also generating their own internal events, you're able to use Carson orchestrations themselves as any other kind of job system. So same thing, the job label, predicates, action block, right? So we call another orchestration as an embedded orchestration in the main orchestration. Let's say you want to build the UI pipeline, right? You want to test that. And then the second handler is when that UI orchestration completes. So all this, the fact that we are able to use the label in another handler, that is where the orchestration engine is working. It's doing the job of correlating an event that comes in with a particular job label in a specific instance, and it's activating the specific handler. So in this case, yeah. So once the UI orchestration is complete, promote the original artifacts into a different release repository on Artifactory. So this promote is a specific Artifactory action. So just an example of the kind of action helpers that are provided by the DSL. Again, more components, right? More of the systems that you're able to dispatch actions to. So let's say after you promoted your artifacts, you want to start your Docker container or run your Docker container on a Mesos resource, right? So start containerized task is one of the job dispatcher functions that we provide. Again, if you've looked at any of these job dispatcher functions, they all, the spec for them is simply, they all end with a job label. So they all expect a job label that you correlate that particular action with. And the other thing is that it's designed for asynchronous operations. So if you're calling an API that's synchronous, it doesn't make sense to wait for something to happen, right? So again, here, a Mesos task, config is a DSL element available to you to get configurational elements given a key. env is a DSL element that's, again, very common, which is to access. So every instance of your pipeline has a map of metadata that is available to it. So you can attach properties. It's just a Clojure map, or in the database, just a JSON. So you can, so a previously defined, so just to be able to use the Mesos cluster, you get access to a Mesos cluster that you're authorized to using the config DSL element, and you provide it a task info object, the Mesos task info protocol that you've previously defined in your orchestration, and the Carson Mesos module, which is able to register all of these frameworks. Given a particular task and the Mesos cluster URL, it's able to submit it to that, and it's able to generate the events for you when the Mesos task is complete, right? Because it acts as a registrar of Mesos frameworks. One of the other common handlers that we have, which is DefListener, which is designed to be at the same level as an orchestration, but it involves not having jobs in it. So it's just handlers that don't end up triggering jobs, but for more synchronous operations and things like that. So for example, if an instance of if your orchestration fails, which is orc_fail is a code.async channel that gets events generated by orchestrations. So in this case, failure events. And then you check whether for that specific orchestration, Jira is enabled. So you can create a Jira issue if an instance of your orchestration has failed, right? Now, just to reiterate, so these were simple examples, where we were able to dispatch actions on some of these diverse systems, but it involved CI/CD applications, right? But you can imagine using this orchestration DSL to create any kind of workflow, things like a workflow to grant privileges to someone in an authorization module, an ETL workflow, right? So, but it fundamentally makes sense, and it's useful when you want to create workflows that are comprised of jobs, like tasks that run asynchronously on other systems, right? Or resource-intensive tasks. Carson itself has an executor, so you can dispatch tasks and actions on the Carson orchestration server. But we try to keep that as the domain of all of these job systems, right? So yeah, just to reiterate that orchestrations can be anything, not just CI/CD pipelines. Of course, some of the systems have very complex state diagrams, which we are not able to map into a directed acyclic graph. So for example, Jira issues, you can go back, you can go, close, reopen, close, reopen, close, reopen, things like that. And that kind of mucks it all up. Okay. So just stepping back a little and why we use Clojure, right? Now, this is kind of like the elevator pitch for Clojure. So I'll just cycle through that. It's Lisp, and we know Lisps are kind of well suited to create DSLs. some of the key things that we found useful for orchestration owners is, Java interop is always available to you. So even if, you're not sure of Clojure, or if you think the DSL is not allowing you to do something, you can use that. We use protocols heavily. The job systems that we previously defined, which are integrated into Carson, are all protocols. So to be able to define and integrate a job system into Carson, as Viraj had previously mentioned, all we need is a REST API or an endpoint that we can call to be able to dispatch jobs, right? And we need an event schema. So the protocol has all of that. What is the event schema that we expect from a particular job system and things like that. And we use macros and multi-methods heavily. Now, I think all of these elements were some of the key advantages that we found in using Clojure to create the service, right? We kept it in a language like Clojure because we thought, because the systems were changing and because we didn't know what kind of systems we would be involved with, we kept it in a language like Clojure so that the DSL could evolve easily as newer systems came in, right? So just a brief example of what is what here. So DefTransition is a macro, successful. So macros are what we use to create some of the basic DSL syntactic constructs. Obviously, all of these macros can be composed on top of each other, so you can create DefTransition my own, right? That uses DefTransition internally, but it looks very different, right? You can make the DSL, you can compress the DSL so that it's just one line instead of, so it's up to you. An orchestration developer can do that. Multi-methods are what keeps our DSL concise. So for example, just looking at this multi-method, which is successful, now in words, it's checking if a particular job, if it has a concept of success, is successful. And we use multi-method here because we are able to use the same predicate function across any type of job or any type of event that supports the concept of a success status, right? So because the events are maps, we are able to dispatch easily. We are able to create the multi-method dispatcher functions easily. And so we use multi-methods heavily to be able to, keep the DSL very concise. So a person who wants to define the orchestration doesn't have to know Clojure all that well. Okay, again, this is a macro. This is an action helper that dispatches jobs. And again, the signature of any job dispatcher is that it expects a unique job label in the context of that orchestration, right? And these are all these are the small number of event handlers that DSL is composed of. It's very simple. And then you can use all of these as templates to build your own bespoke DSL handlers, as I said. Some of the capabilities that a DSL provides you, right? Just functions that you can use in your orchestration or in the action block of a specific handler. So you get a rich set of action helpers, things like repeat and resubmit jobs until a certain condition is satisfied, right? So what this would do is the orchestration engine would submit all the jobs and tasks that were started within this wrapper, and if they failed, it would keep doing that resubmission based on the behavior configuration you've configured. So in example here, you can resubmit in a serial mode twice until it's successful, right? Things like that. Again, timeouts, any job started within this wrapper, if they exceed the duration of the timeout configuration, you can time them out. Throttling protocol, so you can throttle your orchestration. I'm just giving you the basic protocol definition here. But a throttling is when do you throttle and when do you release the throttle, right? That's all the protocol is comprised of. So that's what is available here. So we provide common implementations of that. For example, run only one instance of an orchestration given a condition function, right? And things like that. But an orchestration developer is free to create, reify these protocols or create implementations of these in his orchestration module, right? So trivially, you can provide an implementation policy per orchestration, or you can provide a global one, which is inheritable by all of your orchestrations. This is one of the key things that the orchestration DSL that we heavily use, which is parallel and dynamic job dispatching. So when you have workflows where you don't know how many number of jobs you're triggering in a certain block, right? We are able to encapsulate that into this concept that we call a multi-job, which is a set of jobs which is only instantiated at runtime. So all we are doing is we are giving a label to that set, and we are able to use that label again because the label is the one that allows us to create a deterministic graph for the orchestration. So in this case, for example, we are start jobs. Just looking at this, you can see what the definition of start jobs would be. It's like dosec. So it takes a list, and over the list, it runs all of the forms in it, right? So given a jobs list, we start each of the jobs in there, and then correlate that whole set with an ID called jobs list, right? And we can do skip jobs. So given a certain condition that happens only at the instance runtime, we are able to skip. Similarly, you can do def sync. So if you've started 3 jobs and you want to wait for all of 3 of them to finish, that's what you do. We have a vault, which is an implementation that uses ideas from the crypto vault example in the programming Clojure book that is available to use for any orchestration. So all your secrets can be there. And like I previously said, you can trigger other orchestrations as well. Now, since orchestration is code, and developers want to test their orchestration and their workflow, we provide a test harness, which allows you to create event mocks. So you don't even have to have any jobs created or any systems available to you or any resources available to you, but you can still test the wiring of your workflow, right? So you can still test that, hey, an event came in, this handler should have been activated, this happened, and finally the pipeline ended at a certain point. So you're able to mock those events. I didn't mention it here, but you're also able to mock the dispatcher functions because when you're testing, you don't want to actually trigger a Jenkins job and things like that. And obviously, you can assert on all of these. We do provide a lineagein template as well as plugins. So if you put this in your profiles.clj, you can import the Carson DSL as a library as well as the orchestration engine. And you just do line new orchestration, your project, it creates an orchestration template for you using the lineagein template, and it creates a test template for you as well to test that specific orchestration, right? All you need is probably a local DB, but even that is not needed because there's an in-memory DB that's coming. So that was on the DSL itself. Now, on the orchestration service, the application, obviously, you want to see all the instances for your pipeline. You want to see all the jobs that ran in them. So we have REST APIs for that. We have dashboards that show you that. Yeah, I just want to quickly say what we are looking to do in terms of the future of this project. We want to open source it so we can get more community help. Security and reliability, because the Carson orchestration is a Clojure module. There is sandboxing limitations. Someone can do system/exit in there, which we want to avoid, but we don't want to blacklist too much because you still want the power of Clojure to be available there. So inspection at the load or compile time of the orchestration, runtime detection of issues so that if someone ends up creating an event handler that just loops around, you want to be able to detect that. We want to try out Clojure.spec to be able to specify all of our handlers as well as job systems so that it's more deterministic and we're able to test these workflows automatically as well. And for Clojure newbies, we want to condense some of the DSL constructs. So it's for simple pipelines, you can do that, as well as provide like a UI drag and drop helper. Yeah, that's it. I mean, just to summarize, Clojure has been fun for us in terms of creating the DSL, and hopefully we were able to convey our enthusiasm using Clojure at Oracle. Thank you so much.